Hey, Science 30s. I wanted to go over some of the equations for fields. If you've taken some physics, these will be pretty straightforward for you, but if you've never done them before, they're not too bad. The first one you need to know is the formula for what we call gravitational field strength. Sometimes you might remember it as it's also equivalent to the acceleration due to gravity. But really, though, if you think of a field strength, it's how much force you would feel per kilogram a test mass would experience at a given distance. Okay, so at a certain distance from, say, certain distance from the Earth, if you were right on the surface of the Earth, you would experience a certain force per kilogram of your mass. But if you were out further away, then the force would be less. There'd be less newtons of force per kilogram of your mass. If you haven't studied Newton or force in a while, force is measured in newtons. That's named after Isaac Newton. Um, so anyway, this is the formula right here. And sorry, that's a little blurry. Little g is equal to big G times m divided by r squared. And all the parts are kind of listed there for you. Little g, often little g has an arrow written above it. Okay, like that. But doesn't always have to show that. But that's the gravitational field. It's measured in newtons per kilogram or meters per second squared. You'll see that if you haven't caught it already. Big G it's the universal gravitational constant. It's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Don't worry so much about all those units there, as long as you know what the answer should be in. This number was determined by Henry Cavendish, after Isaac Newton. But that's a number you just use. It's the same every time. You never have to change that. The mass of the source, I have written it in other equations as big M1. But just to remind yourself that it's the big mass, or it's the planet, not the mass of the person standing on the planet. However you want to remember that, but that is the mass. They call this the mass of the source. And then r is the distance from the center of the source. Basically, we measure from center to center. You shouldn't have too much difficulty handling that, because they usually would just tell you the distance or the radius of a planet. So if you're standing on a planet, then the distance from the center is just the physical radius. But the thing to remember is that it is squared. Okay, so that's the formula for, and that's it's in your data table, right? In your data, your Science 30 data sheet, or booklet, I should say. So gravitational force, this one's a little easier. I think this is the force that you feel from the gravitational field, and we call it the force due to gravity. I also like to remember it as weight. So your weight is the force of gravity acting on you. Okay, and weight does depend on your mass, of course, but it also depends on the strength of gravity. So obviously, if you're on the moon, your weight is way less than it would be on Earth. And if you're in deep space, I guess, you could be weightless, because little g, you'd be so far away from any mass that little g is basically zero. Okay, so that formula is the force due to gravity, Fg, is equal to the mass of the test body. So this would be the smaller mass. And you'd multiply that by the gravitational field strength. Okay, so I mentioned earlier that the units, newtons per kilogram, are the units for little g. So when you're calculating the force due to gravity, it's just in newtons. Okay, so let's just look at a couple of these really quick. Or actually, those examples I'm hoping you can follow. They're really pretty straightforward. If you're given the distance and the mass, then you just substitute those in the appropriate spots, and you can solve for g. The trick here that's noted is the keystrokes, and I've emphasized this before. So if you look here, if you have the TI-83s, um, you can test this if you want, but I'm pretty sure it's universal across all the TI-83s. But I don't think you need to use the brackets. Your calculator is pretty smart, and it will um, if you're using that EE button, it will know that you are doing a power of 10 calculation, but you should be able to punch in 6.67 second function EE and then hit -11 and then just go times 5.98 second function EE to the 24th and so on. So I really want you to try that because you should be very comfortable using this EE button because it will save you tons of entry and brackets and everything. And I know for some of you this is new in terms of using your calculator this way. Okay, so uh, let's actually, I'll just maybe go back to that. In this case, it does come out to using 6.37 times 10 to the sixth as your radius. You get 9.83 newtons per kilogram. That radius is an average radius, and if you watch the video uh, on sea level, that one's a really good video. The Earth is not a perfect sphere, not even close. It's more of an oval or kind of bulging out at the equator and squished at the poles. So uh, that radius is kind of an average radius. The number that you may remember is that we use 9.81 newtons per kilogram or 9.81 meters per second squared. So those units are the same, and that's typically what we use for Earth. Anyway, so I do want to take a minute just on this one. So the moon has an average radius of 1.74 to the times 10 to the third kilometers and has a mass of 7.35 times 10 to the 22nd. If we were to determine the gravitational field strength for the moon, we would use the gravitational field strength formula, G equals big G times M over R squared. And we would use this as your mass. Okay, there's the mass of the Earth. And this radius is in kilometers. Now, I know many of you have had to do conversions in other cases. You must get your distances in meters. So don't just grab that number and throw it in. You'll get the answer wrong. You basically just have to times it by 1,000. Now, if you can see the shortcut with exponents, you'd basically just be adding 3 to the exponent. So R would be 1.74 times 10, or just e to the sixth. Okay, but that would get squared. Anyway, if you punch in that number, which you should do, and see if you get this answer, you get 1.62 newtons per kilogram. Or really, it's 1.62 meters per second squared. Compare that to 9.81 meters per second squared. Yeah, the moon has a much weaker gravitational field strength. But I guess that makes sense because the moon is a lot smaller and the radius is also smaller. But really, it's the mass that's smaller by a long shot. Okay, so for part C, if it says, well, then, hey, if you have a 100 kilogram mass and you're throw that on the moon, what would the force of gravity be on that mass? Well, in this case, we would still use, or we would use the force of gravity calculation. So all you would do is take that mass, 100 kilograms, and you would times it by G, which we did 1.62 newtons per kilogram. And no surprise there, this will come out to 162 newtons. That's actually super light, by the way. 162 newtons is nothing. Can almost lift that with easily a couple of fingers in under those conditions. Anyway, so this is really important to remember because it's a very good theory question. As you double and triple the distance from the center of mass, the gravitational field strength gets weaker exponentially, meaning by by powers of exponent. And that is due to the fact that if you look at the equation, r is always squared. So if you double the r, you have to square that 2 and it becomes a 4. If you triple the r, you have to square that 3 and it becomes a 9. So that's what I mean by exponential here. And if you can follow this here, right on this, in this case, it's the surface of Mercury. At the surface of Mercury, it's 3.6 Newton per kilogram. But if you double the distance, so now you're, say, in orbit, and you are twice as far from Mercury as you were on the surface, now the force has been cut by 1/4. So you've taken 3.6 in effect, and you've divided that by 4, because by doubling the distance, it's really 1/2r, but that gets squared. So 1/2r squared would be, the factor would be 1/4, and the same with if you triple the distance. So 1/3r, if you square that, which you have to, it's 1/3r squared. So you'll note that at 3 times the distance from Mercury, the gravitational field has been cut by 1/9. You would have taken 3.6 in effect, and you would have divided that by 9, because that's the equivalent of 3 squared. So the classic shape, which I've seen on a number of tests and whatnot, is this shape right here. So it's a parabolic curve basically, and if you started with a certain value, and then here on the x-axis you could be 1r, 2r, this would be 1r, 2r, 3r, oops, sorry, and so on. Then, if you double the distance, you would go from, say, 100 here, and you would cut that into 1/4. So that would drop you down to like 25. Okay, that's one example. Okay, because you have to cut it by 1/4, and then by 1/3 you would have to drop it by 1/9, and then that would just carry on. Okay, so but that curve is the classic relationship for an exponential relationship, which the gravitational field is. So you're definitely going to get this nice curve here. So that's gravitational field strength. So there's 2 formulas there. No surprise, there's also 2 formulas for electric field strength. Or sorry, just electric field. There's electric field strength and the electric force. And they're completely parallel. Like, they're just using different numbers, but it's exactly the same relationship. The electric field is E with an arrow. Sorry, that did not translate very well. It's actually E with an arrow above it. And that is equal to, we don't use the gravitational constant, we use what's called Coulomb's constant. I should have written that a bit better. It's named after Charles Coulomb. And as we already know, a coulomb of charge, we mentioned him earlier. So this is named after him. But it's a different number, 8.99 times 10 to the 9th Newton meters squared per coulomb squared. You use that number the same every time. This Q is the source charge. So whatever the charge is in coulombs for a specific charge, and then the separation distance is the same in the bottom. Okay, so the formula is completely the same, but using different constants. And now we're dealing with charge now, not mass. So the mass, if you're dealing with charge, mass is irrelevant, essentially. It's not part of the equation. Now the electric force, this one's pretty straightforward as well. The force is measured in newtons. You do need to have the electric field, and all you do is multiply the electric field strength by the charge in coulombs. And so instead of being force is equal to m times g, now its force is equal to E times Q. Okay, so if you can see I think you can see the parallel. Instead of the force of gravity, we're actually dealing with, now they do it that way. I'm realizing that you might think of it in a different sense to make it parallel, because it really should be Q times E. Now, obviously, that doesn't matter mathematically, but um, the parallel comes into this fact that we don't use mass, we use charge, and we don't use gravitational field strength, we use electric field strength. So there's the parallel. I like that a little bit better if that helps you, because those two guys are parallel, are similar, and those two are similar. So we're multiplying the uh, either the either dealing with the mass or we're dealing with charge. Okay, but if you're going to get electric force and fields, you need to use the electric formula. So they're in your data table. I don't think you guys have any difficulty with those once you identify which one you're using. So uh, this I put this in the notes because it's kind of an interesting example. This is showing a moon base, and NASA has proposed a way to shield astronauts from positive particles that are thrown out from the sun all the time. In the solar wind, there are highly charged particles. Well, they're highly energized charged particles, and they're typically positive. Okay, so protons, alpha particles, that kind of thing. And they are coming out with huge amounts of energy. And if they hit your DNA, they can impart enough energy to break your DNA. So we want to protect you from those as much as possible. That's why one reason we wear spacesuits. But the point is here, what they're doing is they're setting up a moon base where they charge these spheres positively. So maybe I'll just show that here. So they'll make all of these big spheres. One trick that they do is they make them all positive. So if they're positive, they're going to have, and I'll sketch this before I erase it. They're going to, basically generate a huge electric field like this, okay, such that any charged particles that come near it that are positive, they're going to be repelled just by electrostatic repulsion. They're going to get pushed away, and so you can see they kind of are shielded away from the those spheres. Now, there's a clever trick that you have to do though, and that is this grid. You can see this grid underneath here, underneath the spheres. This grid is actually connected to some metal rods, conducting rods, and they're jammed into the ground. That grid acts as a shield to protect anything underneath it from that electric field. So really, if these are positive charges, what will happen is a negative charge will be attracted up into this grid. Okay, so that negative charge will come up in from the ground, and there'll be a bunch of extra electrons on the top of that grid. But those electrons will shield anything underneath it. So if you've studied Michael Faraday, it's called a Faraday cage type thing. But that's kind of an interesting proposal. But for an example of how an electric field might be of use, this is one of them. So I'll come back to that in a minute, but I just do want you to see these charged spheres, if they're being developed to protect this base, each one of them could have a charge of 0.02 coulombs. Okay, so that's a pretty good charge. You need quite a bit of electricity to make that happen. Anyway, the first question is determine the strength of the electric field 20 meters from the center of this sphere. So it's just saying you just take one of these spheres here. I know it's a bit grainy, but you're saying 20 meters away from just one of them. How strong would the electric field be at that point? So the solution here is hopefully straightforward once you get used to it. We have the charge, 0.02, and the radius is 20 meters. So then we would enter it into that equation. Now you're going to have to use your EE button like I've been encouraging you to do, but I think you can handle that well enough with some practice. So you'd have to go K, that number is the same every time, times Q divided by R squared. And you'll get a pretty significant force per coulomb of charge. So that's just how strong the electric field would be at that location. And then I think the second question says, consider a second sphere that's also at the same charge. What would the force of, calculate the force of the electric field of the first sphere on the second sphere. Okay, so we aren't going to deal with the amount of force between two charges, But we are just going to simply say, well, if you know the charge and you know the electric field at that location, which we just calculated, then what would the force be? Okay, so this is where you would go E times Q or Q times E, and you'd get a pretty significant force, 8.99 times 10 to the third. That's pretty significant. But anyway, that would be the force exerted by electric field on the first sphere by the second sphere. Now, that means there's a lot of force between these spheres if we had to charge them up this much. So you couldn't just have them, be connected by, like some wimpy rope or just a few bars of, steel of some kind. Like you'd need a pretty robust structure to hold these guys close together because they're going to be pushing each other apart like crazy if they're all positively charged. So that's kind of an interesting. Well, that's part of the answer to part C there. So anyway, that's electric fields. Now let's just end with magnetic fields. Magnetic fields, you need to understand how they work, but you don't need to know the math for them. You don't need to know the formulas for determining the force magnetic, okay? What's really interesting about magnetic fields, if you watch the video, all magnetic fields are generated by moving charges. So if you run current through a wire, then those electrons will generate a magnetic field around that wire. It's really an interesting phenomenon. That's what an electromagnet is. Now, inside an atom, electrons are moving around the nucleus of the atom, and so they actually do generate really small magnetic fields, but they usually don't do anything because those moving electrons and the alignment of their spinning doesn't line up with all the other atoms that are in the same material. So usually it doesn't do anything. But if for objects or materials that are naturally magnetic, those orbiting electrons do align. And that's highlighted in the video about magnets that talks about, how is something a permanent magnet? So first off, let's just look at this. This is showing the current coming out of a cell here, and it's going through a whole bunch of coils of wire. And if you've taken physics 30, you'll know the rule for this, but you don't need to know what the rule is. You just need to know here that the current is going around and around like this, okay? And collectively, there's a magnetic field generated around every piece of wire, but what that produces is a collective north pole at the top of this kind of coil or cylinder and a collective south pole at the bottom. And if you recognize this diagram from the magnetic fields before, the magnetic field always comes out from the north pole and then goes into the south pole as depicted. So, but that's basically, the word is induced. I don't think you'll need to remember that per se, but if the current isn't flowing, then there's no magnetic field at all. As soon as you turn the current on, it induces or causes a magnetic field to be present. And then it'll seriously interact with metals and, attract, a south pole or a north pole or whatever, because they literally just act like a magnet. This little drawing here does show an attempt to show like a non-magnetic metal bar and how inside that magnet, these electrons here are orbiting in random alignments. So you could have they call them domains, if you remember that from the other video, like collective areas or domains. But see, they're totally not lined up, so they don't really produce a collective magnetic effect. But in a permanent magnet, so just a standard lab magnet or like a fridge magnet, all of the orbits for these electrons, as they move, they're all in the same plane, or they all line up. So that means collectively it produces a very strong magnetic north pole and magnetic south pole in the two regions. So you'll always have a north pole and a south pole. You should just know that in general. There's some really cool other explanations for that, which that video does highlight, by the way. You should at least know this, though. The symbol for magnetic field is a B, capital B with an arrow over it. And the units for magnetic field strength are Teslas. It's my favorite unit. But again, you don't need to know the formula. There aren't any formulas that you need to know, at least for Science 30, about magnetic fields, okay? But you do need to know that a that current in a wire does generate a magnetic field. And that'll be really important when we start looking at motors, because that's the reason motors spin, one of the reasons. So I'll just end on this. The Earth itself does have a magnetic field. Inside the Earth's core, there's liquid magma or rock, molten iron actually, and it is spinning because the Earth is spinning. There's a whole bunch of movement, and it's a liquid in the middle. Um, well, I guess, sorry, not right in the middle, but in the very middle, there's a hard iron core, but there's a lot of liquid magma around the Earth. And so all of that spinning and moving of of basically iron means that all those electrons in there are moving, and they generate a magnetic field. And the Earth has a magnetic north pole at the geographic south pole and a magnetic south pole at the geographic north pole. Those are easy to get confused, but it definitely generates a magnetic field that follows the lines as indicated, but it goes out of the north pole and then into the south pole like this. And because the Earth is, orbiting the sun at quite a fantastic rate, I know it takes 365 days for the Earth to go around the sun, but it's covering a really great distance. So anyway, when it comes, as it's moving towards the sun, effectively what happens is all these solar wind particles that are in yellow here, they're come flying in, and the magnetic field does act as a shield. It tends to push these charged particles away from the surface of Earth, similar to an electric field. And what's really interesting, though, is that some of the particles actually get caught in the magnetic field and they spiral in towards the poles, like something like this. Okay. And in spiraling in, they actually hit the second layer of defense. So our magnetic field is a first layer of defense. Our atmosphere is the second layer of defense because it plows in, these charged particles plow into all of the gases in our atmosphere, and they impart their energy to them. And so they kind of get them excited, and is really what happens. And that excitation actually causes light to be emitted. So that's what the northern and southern lights are. There are southern lights as well. We don't hear about those much, but the northern lights are caused by these high energy charged particles that are being kind of captured into a spiral, kind of a death spiral, if you will, because they basically lose all their energy in the atmosphere. So what I'll just end with then is coming back to this, because what NASA proposes to do with this moon base is, I'm going to get rid of the electric field. What they propose to do is they're gonna wrap wire around these loops or around these spheres, so that they, and then run current through those wires. And if you run current through those wires, just like you saw before, then actually, I guess in this case, I did it backwards, but it doesn't matter. This would become a North Pole and that would become a South Pole based on how I drew it. But you don't need to know why it's flipped or around. The point is that it will just generate a magnetic field. So now, in addition to the electric field, which I erased, NASA's proposing that they can also generate a magnetic field, because it'd be really easy to do. It would be induced because of the current flowing through these loops of wire that are wrapped around these spheres that are positively charged. And so you'd get a second force coming from the magnetic field, which would also push those charged particles away. Similar to how the Earth's magnetic field already pushes charged particles away from Earth. And thankfully that happens, so we're not getting pounded by these high energy charged particles that are flying out from the sun in the solar wind. So anyway, there'll be some practice questions coming, but that's an introduction to the formulas for gravitational field, the formula for gravitational force, Fg, and then the electric field formulas and the electric force formulas. Magnetic field is also there, but there is no formulas for that at the moment, and you won't need to worry about those. So there we go.